In our last several conversations, we've been really focused on the edges of the graph. For example, looking for circuits or paths that cross every edge exactly once. Now, in this lecture, we're going to look at the question of moving around a graph from the other side by switching our focus to what's happening at the vertices instead. Now, a Hamiltonian circuit is very similar to an Euler circuit, except it requires that every vertex has to be crossed exactly once rather than every edge. So remember, first, that a circuit is a closed walk that starts and stops at the same vertex and that doesn't repeat an edge. A simple circuit is one that also doesn't repeat any vertices. So when you put all of this together and kind of translate it into simpler terms, a Hamiltonian circuit is one that touches every vertex exactly once, except for the starting and ending vertex, which does have to be the same. And other than requiring that you can't cross an edge more than once, which you couldn't do anyway, crossing an edge twice would mean visiting at least one of its terminal vertices twice, which already breaks the visits every vertex once rule. We don't really have any expectations about the edges. So specifically, some of them may not be used at all, and that's just fine. So let's look at a couple of examples here. The graph on the left does have a Hamiltonian circuit. If we start at V2 and go to V1 and kind of work our way around here, V4, V3, and then back to V2, we have a circuit that crosses every edge. We have a circuit that touches every vertex exactly once and that starts and stops at the same place. So that one does have the kind of circuit that we're talking about. Specifically, if you write it out, like write it out with just the vertices. Normally we put the edges in there as well, but in this case, at every vertex we end up at, there's only one way to get to the next vertex. So it's clear just from the context what the edges are, so it's kind of okay to leave them out here. Now, this bottom graph, this one doesn't have a Hamiltonian circuit. And if you play around trying to find one for a minute, you quickly realize that vertex V2 there is a problem. It's a bottleneck. Once you cross that vertex and get to one side of the graph, there's no way to get back to the other side to close your circuit. Right? We'll talk a little more. We'll make that a little bit more formal in the next slide here. But bottom line, that graph doesn't have the kind of Hamiltonian circuit that we're talking about here. The mathematics of Hamiltonian circuits is very different from what we saw with Euler circuits and Euler paths. In the Euler case, we were able to come up with some very straightforward tools for determining whether or not those particular kinds of paths existed in a graph. Unfortunately, there are no such criteria for deciding if a graph has a Hamiltonian circuit. In fact, there aren't even any known algorithms for finding such a circuit in a reasonable amount of time when the graphs start to get big. And we'll talk some more in the next lectures about what exactly is meant by a reasonable amount of time. So we do, however, have this theorem here. And I want to be really specific about what this says and what it doesn't say. This does not give us a tool for determining when a graph has a Hamiltonian circuit. Right? The theorem starts out, if a graph has a Hamiltonian circuit, in other words, if we already know that such a circuit exists, then the graph has these properties. It has a subgraph that first contains every vertex of the original, is connected, has the same number of edges as vertices, and every vertex of the subgraph has degree 2. So we can use this theorem for is we can use it to determine when a graph does not have a Hamiltonian circuit. Because remember, if a conditional statement is valid, then so is its contrapositive. And the contrapositive here is going to be if a graph does not have a subgraph with these properties. In other words, if so much as one of those properties can't be satisfied by any subgraphs, then the graph does not have a Hamiltonian circuit. Okay, so the proof of this is actually pretty straightforward. It really just relies on the definitions of some of these terms. Right, so say we have a graph and it has this Hamiltonian circuit. Right. First, notice that it starts and ends at V1. Right. It does start and end at the same place. And what I'm going to do is I'm going to claim that the subgraph defined by this collection of vertices and edges has the required properties. Okay, first, it has to contain every vertex of G because a Hamiltonian circuit has to touch every vertex. It has to be connected because this is a circuit. You pick any point and you can get to pick any vertex and you can get to any other vertex just by following around the circuit. It has the same number of edges as vertices. You notice that there does seem to be a one-to-one correspondence. For vertex 1, edge 1, vertex 2, edge 2, and so on. The only way we can have something repeat here, the only way we can have the number of edges and vertices not be the same is if either a vertex repeated, but that's not allowed, because the vertices can't repeat in a simple circuit, or if one of the edges repeated, and that's also not allowed because the edges can't repeat in any kind of circuit. So we have a one-to-one correspondence here between the vertices and the edges, which means we have the same number of each. And every vertex has degree 2. I mean, again, you can see as a circuit where none of the vertices are allowed to repeat. Every vertex has an edge coming in and an edge coming out. And now, if you look over at the graph here on the right, this is the first graph we looked at in the previous slide. You can see that this particular Hamiltonian circuit, which I've highlighted with the arrows, does satisfy these properties. The subgraph defined by V1, E4, V4, E3, and so on around that circuit. It contains every vertex of G. It's connected. It has 4 vertices and 4 edges, and yeah, every vertex is of degree 2. Good, so it's kind of confirming we can see the theorem working here. So let's take a look at the other example. And we can see how we can use this theorem to show that this graph does not have a Hamiltonian circuit. Right? So start by thinking about a subgraph, right? And we know it has to contain every vertex of G. Right? So it's got to contain V1, 2, 3, 4, and 5. And it has to be connected. All right, so here's what I'm going to do. I'm going to try to build this subgraph by adding in edges. Right, so let's say we start at V1. Because the degree of V1 in my subgraph has to be 2, I have to add 2 edges coming out of it, and I only have one option for each, right? It has to be E1 and E2. Okay, well now look at vertex 3. For vertex 3 to be degree 2, I have to add vertex E3. And now I've got a problem. Right? I'm not done. I have to get over to vertex 4 and vertex 5 somehow. To do that, I'm going to have to add either E4 or E5, and that's going to mess up the degree of E2. It's going to make it something other than 2. Now, which means it doesn't satisfy the criteria. Right? Now, technically, you need to make the same kind of argument for all 5 vertices, but there's a lot of nice symmetries going on here. The same argument is going to work for vertex 3, 4, and 5. And you can do a very similar argument. I'll leave it up to you to think your way through. But you can make a very similar argument to see why we also run into trouble if we start at V2. All right, so that's how this theorem can be used to show when a graph does not have a Hamiltonian circuit. So the next lecture, we're going to look at a classic graph theory problem related to Hamiltonian circuits called the traveling salesman problem. And this will give us a context for looking at some algorithms for finding sort of a Hamiltonian path. Right? While these algorithms may not be able to guarantee the best results, they usually give good results, and they have the upside that they're going to do it for us in a practical amount of time. So there's a link to that presentation below, and if you like this lecture, please don't forget to click on the like button as well.